In this video, we start our discussion on linear programming. I give an overview of the types of problems that are best addressed by this technique. Linear programming is about discrete optimization problems. In such problems, the variables are assumed to take only discrete values. This is a very large field of research with many branches. We will focus on the following type of problem. We need to optimize a function f with variables x1, x2 up to xm such that at the same time several constraints are satisfied. The constraints may be of several types. We may have a few greater than inequalities over variables x1 to xm. We may have a few equalities. And we may have a few smaller than inequalities. Here is an example of such a problem. Let's assume that we have a carpenter making tables and bookcases. The question he faces, obviously, is how many of each should he make each week to maximize his profit. I'm going to denote the tables that he should make by x1 and the bookcases by x2. So here is what we know about him. The profit that he makes for each is, for a table he makes $25 and for a bookcase he makes $30. The amount of lumber he needs is, for a table, 20 feet and for a bookcase 30 feet. And the work that goes into each is, for a table, 100 minutes and for a bookcase 80 minutes. And he has each week firm contracts that he needs to honor for 4 tables and 2 bookcases. Each week he has available 600 feet. And time to work each week is 40 hours. So here is how we formulate our problem. He wants to maximize his profit, so the objective function is going to be maximize $25 times x1, which is the profit he's going to get out of making tables, plus 30 times x2, the profit from the bookcases. The amount of lumber he uses has to be under 600 feet, so that means that 20 times x1, which is the amount of lumber goes into making tables, plus 30 times x2, this has to be smaller than or equal to 600. He only has at most 40 hours to make his product, so I divide this just to transform from minutes to hours. So 100 over 60 times x1 plus 80 over 60 times x2 has to be smaller than or equal to 40. And this can be now simplified and rewritten into, so just this equation can be rewritten into 5 over 3 x1 plus 4 over 3 x2 is smaller than or equal to 40, but I can also rewrite this one more time as 5x1 plus 4x2 smaller than or equal to 120. And obviously he has to make at least as many as his contracts require, so clearly we will have to ask that x1 is at least 4 and x2 is at least 2. Many optimization problems become quickly so complex that they cannot be solved. In such cases, we are left with the option of looking at approximations. We will focus in this week's videos on simpler problems that can in fact be solved and that are very useful in practice. Linear programs. A linear program is one where we only have the objective function and all the constraints are linear and contain no parameters. And the variables take values over rational numbers. Such problems are called integer problems if at least one of the variables is required to take only integer values. Here is another type of optimization problem called dynamic programming. This refers to a problem where not all decisions have to be taken at the same time, but they can be taken in stages. Here is an example. We have a rancher and he has an initial herd of K cattle. And he will want to retire after n years, and when he does that, he will sell all remaining cattle. Each year he has a decision to make on how many cattle to sell, and he will generate a profit Pi in that particular year. The number of cattle that he keeps in year I is going to double in year I plus 1. And so this is the characteristic of the problem. Each year he will have to take a local decision of taking a larger profit versus building the future, but the optimization goal is a global one concerned with the profit after n years. The focus in the remaining of this week's videos is going to be on solving linear programs, and we will consider geometric solutions, algebraic solutions, and some elementary considerations on the simplex method.